morning, everybody. It truly is an honour to be here today and to have been invited to present at this workshop. I've lived out east since '95 when I first moved to Canada, but most of my work has actually been in Alberta and Western Canada, so hopefully some of my experiences are relevant for this province and today. Please bear with me, I'm just getting over a cold. I think I can handle the next hour, but my voice is a little bit tickly at the moment, so if I pause every now and again, you understand why. So I was asked to give a 1 hour outline of essentially airborne laser mapping. Out east at the Centre of Geographic Sciences, myself and my colleagues put together a 20 lecture course, which was basically an introduction to LiDAR systems. So some of those materials I'll be recycling here today. The difficulty was, of course, trying to condense a 20 lecture or 3 hour lecture series into a 1 hour overview. So hopefully the slides I've selected will resonate and be a little bit will be appropriate today. In some ways, my presentation is a little bit backwards because I'm going to start off with applications and then we're going to move more towards the technology later on. I felt it was a little bit illogical to start by introducing the theory and technology before people really understand what it's about. I understand this is a diverse audience, so it's probably a range of expectations and background knowledge. So hopefully if we start with applications, then at least we know what it's all about. So the first question I usually like to ask is, so what does an airborne laser scanner do? And I'd like to put that one out there. Would anybody like to hazard a guess? I'm sure we all have ideas, but does someone want to throw out a suggestion as to what an airborne laser scanner is all about?
Just pick somebody.
Keith.
Oh, gee. It scares.
It scares. No, it does, absolutely. The response that I often get is it creates DEMs. And that's true, of course, but it's a lot more than that. Airborne laser scanners map ground surface coordinates at very high resolution. But I also like to add this little addition of near ground. It's not just about DEMs, it's not just about the ground surface. Airborne LiDAR systems create a point cloud, and they give us a very rich information or a data set of the three-dimensional environment of the ground and the surfaces above the ground. But of course, LiDAR is great for DEMs, and DEMs is the primary data product that is derived from LiDAR data. For example, this is a digital elevation model from the Lake O'Hara watershed just near Lake Louise. This data set was captured in around about half an hour of airborne survey time, and it really didn't take too long to process it either. So when you compare that with photogrammetry, the efficiencies and the accuracies are quite obvious. So for example, here we have an air photo. I apologize, it's not a particularly great air photo, but it serves to illustrate a point. Now from stereo pairs and traditional photogrammetry, we can generate a triangulated irregular network model of a digital elevation model, strip away the vegetation. But one of the problems in forested areas, of course, is that the ability to see the ground beneath the trees is somewhat limited. And so we end up with what we can see here, a fairly faceted model, fairly low resolution representation of the ground surface. With LiDAR, of course, because it's an active illumination technology, we can capture far more points beneath the canopy and generate a much more higher resolution DEM. So in essence, that's one of the values of LiDAR over traditional photogrammetric methods for DEM generation. This is a rather old slide that I've borrowed here, but again, it serves to illustrate another point. The solid lines that you can see here, I apologize, I'm probably going to defer to this one because I can see it a little bit better. The solid line refers to the LiDAR data, the dotted line refers to photogrammetric data, the left axis is dollars per square kilometer, and the bottom axis is the area of data coverage. The numbers aren't really important, but the point is that the initial acquisition costs for LiDAR for a very small area are quite high. This is an old study, but it's still true today. Because the technology is more mature and more cost-effective, photogrammetric data collection can be quite cost-effective over very small areas. But the point to be made here is that once you get to larger and larger areas, those initial costs, like the investment costs and the overhead costs associated with a LiDAR survey, come down. And so for much larger areas, the costs of DEM generation at a given accuracy level, a given contour definition, 1 meter or 2 meter in this case. But once the areas get large enough, then the LiDAR costs actually become more competitive with photogrammetric techniques. And so for higher accuracies, the LiDAR data tends to be more cost effective. Now in terms of public product availability, DEMs, wide area coverage, there are certain public data sets that are out there. In Canada, we can access GeoBase and obtain digital elevation models for the whole country. Same goes for the US, and this is just one example of I apologize, I don't know the area exactly, but this is color infrared photograph, again borrowed from another presentation, of a valley area in the western United States. Now the USGS, of course, has a 7.5 minute or 30 meter by 30 meter digital elevation product, and this is what that looks like. So these types of data products are publicly available. But if we compare that with LiDAR coverage in the same area, of course it's obvious that the amount of detail and the feature extraction capability of the LiDAR data is much superior to what's publicly available. The other advantage, of course, of LiDAR is we don't just capture the ground surface, we capture whatever surface is encountered. So in this case, we see a digital surface model of a canopy, buildings within a floodplain, and of course, we then have the ability to strip away all of that detail and obtain the terrain that underlies the canopy and the buildings. But it's not just all about rasters, it's not just all about digital elevation models and digital surface models. It's really about point data. This is what the airborne laser scanning system actually captures. It captures points. What we do with the points afterwards is up to us. DEMs is just one application. But of course you can see here, in this particular example, and again I apologize because I really don't like it when I can't acknowledge the source. I found this image somewhere, it's a great image, and if someone knows where it is or who captured this image, I'd really like to know. But anyway, it's not one of my images. But what you can see here is there's a lot of detail on the sides of the buildings here in this urban environment. So there's more than just a top-down view here. There's a lot of vertical structural information contained within the data that's lost as soon as you turn the data to a raster, either a DEM or a DSM. Just to serve as another example is a screen capture from one of the software packages that we utilize a lot. In this case, it's TerraScan. And here we can see a plan view of a crane over the Halifax Harbour area. And here we can see cross sections through the same cranes. So of course you can see again, here's this vertical structural information. This is not a particularly special airborne LiDAR data set. It's not exactly as dense as it could be. I think in this case it may be 3 or 4 points per square meter. We can capture 20, 30, 40 points per square meter if we really want to. So the information content, even in a fairly moderate LiDAR data set, can be quite high. And it's not just about elevations, it's not just about coordinates. What this image illustrates is we've got a point cloud, so we can see the color variation is the elevation of the point cloud, but then the total variation, or the brightness in the image, is actually the signal strength or the intensity. So we can simultaneously visualize the elevation content within the image, but we can also visualize the brightness of that image. And why is that useful? Well, in this particular case, this is a coastal environment, so here we can see the coastline, and here we can see a river, and here we see a wetland environment, and here we see a road. Well, all of these areas really wouldn't stand out if we were just looking at elevation variations, because the elevations of these features and the adjacent terrain is very minimal. But in the brightness, there's a huge difference because the signal strength is somewhat a function of the surface that it encounters. Most airborne LiDAR systems, not all, but most, are a near-infrared laser-based system. And so what we're seeing is the reflectance in the active near-infrared. So in this case, you see the wet areas are dark because a lot of the energy is absorbed. And the highway is also dark because it's an asphalt surface, and again, a lot of that energy is absorbed. Whereas the vegetated areas come out fairly bright in this particular image. Now here we have a raster of the elevation and the intensity data transposed. So pretty much exactly the same as what we've just looked at in the last image, but except it's been rasterized. But it's the same information content, except it's over an urban area. The reason I chose this slide, and this is actually a sales slide from Optech Incorporated in Toronto, is because we can even see road markings. Now this is a LiDAR image. Color variation, again, is the elevation. So the blues represent this floodplain here. The red represents these building groups. But then the brightness represents things like street markings, the road center lines, parking bays, moisture on the roof of these buildings, and things like that. None of these things would come out in the coordinate information alone, but they come out in the intensity information. So when you put these two streams of information together, you get very, very rich information content. It's becoming more and more popular to fuse LiDAR data with other sensor technologies. It's almost standard today to acquire LiDAR data with a camera, as long as the acquisition conditions are correct, time of day, that kind of thing. And in this particular case, what we see is a 3D point cloud, but it's being color-coded with RGB information collected from a camera that was acquiring data simultaneous to the LiDAR. So every single one of the points that are in there, and I don't know how many there are, but obviously there's a few tens of thousands of points in there. Every point has an XYZ coordinate. It has an intensity measurement associated with the signal strength of the returned laser pulse, but it also has a red, green, blue channel information content, which allows us to generate this three-dimensional color point cloud. So what else can we do with point clouds? We can generate building models. The next few slides, I'm just going to give a few examples. It's just some of the work of a couple of my students from a few years ago. Actually, I think some of the people in this audience might recognize these names, Alison Fox and Lee Larder. We'll talk a little bit more about building models later on. Powerline applications, mapping the catenaries on the power lines, mapping vegetation encroachment, comparing the as-built to the design specification of transmission lines, are all areas where LiDAR has really accelerated its growth over the last couple of years. And one of the main reasons for that is because in the US, the NERC, the North American, I forget the acronym, Energy Reliability Corporation, put out some recommendations to the industry, which essentially suggested that, well, you really need to use LiDAR to check these things, the as-built versus design, the vegetation encroachment, or the power line hazards, that kind of thing. And so that led to a real rapid growth in the adoption of LiDAR for transmission line monitoring. And so actually that's probably one of the fastest areas of growth, at least in North America right now, is the application of LiDAR for power line monitoring. So this just gives an example of, we can classify the towers, the catenaries, and all the features around there. And the software setup that's dedicated to doing that task. Flood impacts. Flood impacts is probably one of the applications of LiDAR that really pushed the industry in the early days, partly in response to FEMA, the Federal Emergency Management Agency in the US, put out guidelines very early on for how LiDAR could be utilized for flood mapping, both in a coastal zone environment and in an inland riverine floodplain environment. So here we can just see an example of, if you take the DEM, in this case it's a hill-shaped representation of the DEM, and then transpose on top of that a hydraulic model, hydraulically modeled surface of the flood waters running through there. You can then estimate the flood depths at any point within that area, and so that's what the various shades of blue represent is the depth of the inundation. One application that really hasn't been utilized very much, is still somewhat experimental, is the utilization of LiDAR for water level assessment. And this probably is not a particularly commercial application, but it does have some research value. This slide just illustrates a study we did over the Mackenzie Delta back in 2008. Did a number of surveys up in the outer delta, and a number of transects across. And for each one of these areas, we had validated with gauges that monitored the water levels. And so what we wanted to do was both validate the LiDAR estimation of water level, but also to see if there were any interesting variations in water level within these within the delta. And it was a large study. There were a lot of interesting things we observed, but one thing that kind of stood out was that in some of these kind of flow restriction areas, we actually observed kind of backing up of the water level, such that the water levels actually seem to rise and then go down. And this was not something that you would be able to capture in a standard hydrometric network. The only way you can do that is if you simultaneously map the water levels along several kilometers of river reach. So from a hydraulic point of view, the ability to almost instantaneously map water levels along these river reaches was quite profound in terms of what it could tell us about hydraulics of that environment. So this is research, and I'm not suggesting these are commercial applications, but from a research point of view, this is quite useful. More northern work, but coming a little bit south from Nunavut. We've been, since 2006, we've been flying surveys over the Northwest Territories. And one of our areas of interest has been trying to understand the interaction between canopy and permafrost. And so in one study area in particular, near Fort Simpson, we've done some fairly intensive investigations of the canopy and the permafrost in situ. I'm not doing this, colleagues of mine are doing the in situ work. But what we've done is we've tried to map the canopy attributes and come up with automation algorithms to extract permafrost plateau extents, because morphologically these features are very distinct. And of course, LiDAR gives us great morphological or geomorphological information. And so this lends itself to generating scripts or automation routines, such as you can see here, an edge enhancement routine to extract these plateau areas or these upraised permafrost features, and then do more analyses. To do this manually would be very time consuming, but to have an automation routine, because the data is directly digital, actually improves our ability to do the analysis objectively and rapidly. Landslides, hazard applications. Back in 2007, we happened to be in Whitehorse in the Yukon, and a few days prior to that, there'd been a large landslide off Mount Steele. Mount Steele is the 5th highest mountain in Canada, 5,100 meters. And as you can see from the imagery here, well, I hope you can see, there's a large scar in the north face of this peak. That was as a result of a landslide that came down in late July 2007. We just happened to be there, so we flew. It was actually quite a challenging survey, because you're up at over 20,000 feet in an unpressurized survey plane, and the range from the top of the mountain all the way down to the bottom was approaching 3,000 meters. Was around about 3,000 meters or 3 kilometers, which is the vertical range capability of the LiDAR sensor that we had. So clearly we were unable to survey the top and the bottom of the mountain at the same time. So we essentially had to fly lines and stagger the lines down all the way in order to capture this LiDAR DEM. Unfortunately, we didn't have a LiDAR DEM that predated the landslide, but through GeoBase we were able to obtain the NTS data. And that's not a simple thing to do a comparison when one data set is from photogrammetric sources from the 1970s. And there's a lot of other things going on there. But anyway, we can see here the red in this image, in the image in the bottom right-hand corner. The red illustrates the scar within the mountain. The blue represents the deposition at the bottom of that slide. And so from these estimates, we're able to, from these measurements, we're able to estimate the volume of, of that landslide, which would be somewhat challenging to do otherwise if you went out there with a survey tripod and tried to measure it yourself. Now, one area of study that's fairly close to my heart is the glacial water resources in the Rockies. Ever since 2000, we've been flying LiDAR over the Water ice field. And I'm sure many of you have driven the Icefields Parkway and have gone up to the lookout and looked at Peyto Glacier. Well, this is Peyto Glacier from 2000 to 2010, I believe. And what you can see in the image on the left is the vertical down wasting each year throughout that period. And if you look at the scale, we're looking at up to 40 meters of down wasting over that 10-year period. So that's quite a lot of ice that's been lost out of that one glacier during a one-decade period. Now, if you look at the image on the right, I'm not sure if you can see it very well, but this is actually a time series for the same time period, but it's of the hillshade. So what we can see here is the morphological changes within that landscape. So we're not looking at vertical changes, looking at the morphological changes. So what we can see is the shrinkage of the glacial margins. And we can also see that the slopes around the side of the lateral moraines around the side of the glacier are actually sliding down or slumping in towards those margins. So with time series analyses from LiDAR, we're actually able to get some very high resolution and high fidelity information on morphological changes. We can measure the rates of changes and we can measure the volumes of changes. Sticking with the Alpine and the Rockies, another change detection study we did back in 2007 and 2008, and this was funded by Sustainable Resources Development, was to assess whether or not we could map snowpack depth within the mountainous environment. I'm not going to walk through this entire slide, but this is the Marmot Creek in the Kananaskis area. Here's a snow depth map from a summertime and an end of winter or late winter LiDAR survey, which was one image subtracted from the other. And these graphs in the top right-hand corner just illustrate the data quality. It is by no means perfect. There are some challenges with trying to map snow depth. Not least, snow isn't necessarily all that deep in many places, and you start to get down to close to the noise level in the LiDAR data. And particularly in forested areas, it's very noisy. And there's a lot of reasons for that, primarily because of the understory conditions. But up in the Alpine, the results are very encouraging. We're able to map snow depth to a high degree of accuracy within the Alpine environment, and also within fairly open valley environments. So I think there's some potential there. It's not perfect. It's, I'm not recommending that anybody goes out and starts mapping snow with LiDAR in the Alpine right now. It's a lot of challenges, quite costly. But I think as the technology improves and as costs come down, snow depth monitoring, either for a resource or a hazard application, does have potential. Maybe not today, but give it a couple of years and we might be there. More change detection. A lot of us here are probably interested in growth and yield and forestry applications. Again, we can do temporal assessments over forest canopies and we can monitor growth. And with one of the studies we did, we found that you need at least a 3-year period to ensure that the estimates of growth that you obtained from this type of methodology were significant. Anything less than 3 years, like if you measure canopy 1 year to the next, it's probably not going to be very accurate. And of course, it depends on the rate of growth. In this particular example, we're looking at a canopy that was growing around about 25 to 30 centimeters per year. So anything less than that, your time period would be longer. But if you've got about 25 to 30 centimeters of growth per year, then after 3 years, you're approaching a meter of growth. And at that point, that's where you start to get statistically significant estimates of growth rate. So that was an important finding. Sticking with the forestry theme, and also kind of broadening out the scale a little bit, one of the studies we did recently was to assess biomass within the whole province of Nova Scotia. Admittedly, Nova Scotia is a lot smaller than Alberta, but it's still a rather large area. 50,000 square kilometers, I believe, or something like that. Now clearly we don't have LiDAR for that entire area. Whilst I was at the Applied Geomorphic Research Group, we did survey around about 20% of the provincial coverage, and we've been flying transects over much of the province for that time period as well. And so what we were able to do was link the LiDAR data with the provincial permanent sample plots and develop models of biomass, and then apply that to the forest resource inventory data for the whole province and come up with a spatially explicit estimate of biomass for the whole province. So that was one example where the LiDAR was not used to do all of the modeling. It was just used as a piece of the puzzle to help calibrate the models. I'm sorry, I don't see a clock anyway, so I'm just going to have to check the time here. Okay, so that was just a very quick overview of a number of applications that are out there. And I didn't want to focus on the more obvious applications that you've probably already heard about. I want to stick with some of the more esoteric applications that are maybe not commercial yet. But obviously there's a lot more. You know, highway development, urban development, mining, cut-fill operations, those kinds of things. Those are all standard LiDAR applications that are commercially implemented today. So there's a lot more than I've just mentioned there. Before we discuss the technology and theory, which frankly I find a fairly dry topic anyway, I thought I'd discuss a little bit about the market, because growth, who the users are, what the value of LiDAR is for the community at large is probably a relevant thing to get a handle on. So essentially this section is about who cares about LiDAR. Back in 2009, a market study was published, and it's widely available. Anyone can obtain this survey if they so desire, by Carrier Associates in the US, that tried to look at all of the aspects of the market and where the market was at. In this first slide, what we can see is that the user distribution is heavily biased towards government agencies. In this particular sample set, we see that 55% of the respondents, and this is a very open survey, so this is somewhat representative of the community at large, 55% of the respondents were either municipal, state, provincial, or federal agencies. And so that indicates that that's where a lot of the work actually is. In terms of market growth, prior to 2005, I think the only indication available was this study by TMSI, and I forget the acronym. But again, this was another market study. And this was just of the number of sensors that are being sold. So a very coarse indication of the market growth, but nonetheless it illustrates the point. In 2000, there were less than 40 sensors out there and commercially deployed around the world. By 2005, we were about 110. And so that represents about a 50% growth over 3 years. Now, since 2005, the Carrier Associates report came out, and they looked at a few other indicators, and they looked at, they stratified the market by different parts of the world. So if we look at the census example, in 2005 we got from 110 to 192, which again represents around about a 50% growth over 3 years. And that level of growth is also reflected in the number of operators or service providers and the amount of expenditure within the market. So what we can see is by 2008 we were spending about $300 million per year on LiDAR. Right now it's around about $500 million per year. That's just on basic acquisition. So all of those indications suggest there's around about 50% growth over 3 years. Whether that's still the same today since 2008, no, the market's changed quite a bit. I don't know. But the interesting thing is, since that report, there's no reason to believe that the market has diminished any, because a lot of federal funding in this country and in the States and around the world went into infrastructure development. Infrastructure development is where a lot of the LiDAR survey work is directed. So actually it's possible the growth during that time period has increased. And also the new recommendations by NERC, the North American Energy Reliability Corporation, actions like this actually suggest that the market might have grown even more than than what's suggested in previous data. Now, sales trends, another dry statistic, but the point here is that more than 80% of respondents in all sectors, whether it's software providers, hardware providers, data processors, or data collectors, more than 80% of all respondents indicate that their own business has grown. And most of them indicate 10 to 20% per year. So it seems to be a fairly healthy and vibrant market. So respondents were asked what are the likely trends over the next 3 years, 2009 to 2012, or till today. And it was suggested at the time increasing point density was going to be the top trend, decreasing costs of data, easier or improved post-processing and analysis software, multi-sensor data fusion, and larger scale data acquisitions, provincial, statewide, national. And here we are in 2012, and I would say all of those predictions were true. All of that has happened and is still continuing to happen. Okay, now I'm not going to list off all of these business uses. We could call these applications. But this was another study that was recently presented at the International LiDAR Mapping Forum in Denver a few weeks ago. And again, this was another study that was put out to the community. And the question in this particular case is, what are the primary business uses for your department? And so they compiled a list. The list itself isn't really important to the point I'm trying to make. The point I'm trying to make here is, in that particular study by Sugarbaker, Snyder, and Moore, they wanted to essentially do a cost-benefit analysis. Again, given the costs of LiDAR acquisition are considered to be quite high, if we did this at a national scale, and this is for the US, but if we did a LiDAR mapping campaign for the whole of the US, what would the potential benefits be? So they did a fairly extensive study, and they categorized, they did a cost-benefit analysis for all of the different application or business uses, and they came to the conclusion that a conservative estimate of the national benefits, after factoring in all of the costs, would be about $1.2 billion per year. I couldn't possibly explain how they arrived at that number, but that was their conservative estimate. They believe the potential benefits approach $13 billion per year. And that's across a wide range of applications related to resource, infrastructure, and hazards, and many other applications.